As of now, it is 11:14 p.m. on 29th September 2025 in Shanghai, and I am doing CG3207. So what I'm going to be doing today is assignment 2, which is basically on implementing a rough RISC-V CPU, and I'm going to be doing a rough demo on like the CPU and the assembly code that I wrote to demonstrate the instructions. Yeah. So firstly, I have the Nexus board here. And yeah, when you turn it on, it powers up the standard program, or at least it's supposed to. Not too important anyway, because what I'll be doing is that we'll be uploading our bitstream. And yeah, so this is our RISC-V CPU implemented using the given wrapper. And I've made an assembly code to demonstrate various instructions. And the instructions include, if you can see on the website here, add, the load word, store word, BQ, BNE, JL, and basically all of this. So mainly arithmetic instructions, jump instructions, load from memory, store from memory, all this kind of things like that. Yeah. And the way I do this is by making a simple calculator program. So long story short, you use the dip switches to enter in values. After that, you then use the buttons to like confirm the values, and then with that you can then get the final result output on the 7-segment display. Okay, so let's get to it. So in the program there are a few modes, about 11 modes actually. So let's start with the add instruction. So there are basically 4 stages to the program. I guess I can take some time to show you, at least try to show the program itself. So the first part is basically initializing all the memory mapped IO locations in the registers, and afterwards, okay, this isn't exactly too important. Afterwards, we wait for a push button to be pressed, and so you can notice that there's the BNE instruction, which basically it loops until the push button memory map value is equal to 1, which means that a push button is pressed for simplicity's sake. And then afterwards, you read the value from the dip switches and you store it in a relevant register. You do so again for the next push button, read another value. For the next push button, read another value. And for the next push button, read another value. So you read 4 values in total. The first value is a mode setting, and then you read 3 other values which are used in computations in like these various modes. And they are used in computations as such. Okay, and then afterwards is output on where? Both the LEDs and also the 7-segment display. Yeah. Okay, so now let's start. So now we can firstly demonstrate the add instruction. So the add instruction has a mode of 0. So what does that mean? All the dip switches should be 0. And then afterwards we can press this first button. Okay, very good. Once the button is pressed, the mode setting is the value is reflected on this part of the LEDs at least. So let's say I want to add 1 plus 2. So the first value I want to add is 1. And then I'll press the next button. Okay, 1, that's good. I want to add 2. So I press this button. I set this dip switch, which is 1, 0, which is 2. And then afterwards, I press this. And then it sets to 2. And I actually can input in a third value, but in this case, it's not very important. So I can just set it to, let's say, 4. And then I press the button again, and then 1 plus 2 equals to 3. So this shows that my add instruction is working. Alright, that's good. So now we can briefly do for the subtract instruction. So firstly, we set the mode. Mode is 1 in binary, so it's 0. So it's like everything is 0 until 1. And then afterwards, we can set like, let's say 4 minus 2. Okay, so 4 minus 1, that'll be more interesting. So 4, and then minus 1, and then afterwards the other value doesn't matter. Okay, it still computes. I just realized that this actually gives back the same result, so maybe they can try another different value, maybe 8 minus 1. So set the mode setting to 1 again for subtract. 8, 1. So we get 7, which is what we expect. So those are add and subtract. The next instruction I want to go through is this AND instruction. So it's basically like a bitwise AND. So the bitwise AND mode is 2. So we can do this first. And then afterwards, let's say we can just put like some random dip switches here. So like 4 dip switches here. So 4 light up here. And then we can put these 2 dip switches on here. So you notice the overlap is these 2. And then of course the remaining value we don't care. And with AND, just as a reminder, we should only get these 2 on because it's a bitwise AND. Yeah, and there we go. So now we're moving on to the OR instruction, which is the next mode. It's mode 3. So we can do this first. And then afterwards, mode 3, we can, let's just input in the same values. Okay, so now all these LEDs are on. That's great. So that's AND and that's OR. Now for more interesting instructions, I guess, which is shift left, SLL, shift left, and then SRL, and then SRA. Those are problematic. So for SLL, right now the program is coded to only look for like the values you input in value 1 and value 2. So it's mode 4. Mode 4. Okay, so mode 4 is here. So we enter in the mode first. And then afterwards, shift left. So shift left is shift it this way. So maybe you can start with something small. Maybe you start with, let's say, a value of 1. And a value of 1, let's shift by 8. So let's shift by 8. And then the last value doesn't matter. Okay, so 8 bits. So actually, I think you can see it from here, which kind of makes sense, which, if I remember correctly, this represents a value of 256. As for so for values you can see on the LEDs, let's try again. So mode setting 4. So maybe we can try like this certain pattern. So yeah, this certain pattern. And then let's say you want to shift it by 2. Okay, let's shift it by 3 actually, so it'll be more interesting. So if you shift it by 3, so these 2 from here, it'll be shift 1, 2, and 3. So this is LED 6 and LED 4. Yeah, LED 6 and LED 4. Okay, so now let's shift by 3. Last value doesn't matter. Okay, so LED 6, LED 4. So this is left shift. Alright, so the next one is SRL. I was trying to find a good way to explain how to do SRL, but SRL is a bit problematic because to do SRL and to do SRA, the important thing to show is the sign extension. And the registers are the 2-bit values, so it's not very easily inputable on like a 16-bit dip switch directly. So the conclusion of what I did was that's why we input in 3 values. The first two values comprise the first value, the first operand, and the last value, value 3, corresponds to the bit shift. And so SRA is mode 8. So you can start by inputting the mode first. And let's say SRA is, if I remember correctly, is arithmetic, so there is a sign. Yeah. And let's do it. The first few bits that we input in is actually the MSB. So it's like, so let's say this is a 32-bit number, is this upper part. So this includes the sign bit. So just for simplicity's sake, let's just turn everything on. So all on. And then the next value is the LSBs of the first operand. So we can do something like, if everything is all ones, we'll get a value of -1. So, and then after that, we can, let's say, in the interest of simplicity, we'll just like turn off these values. Or maybe we'll do a pattern. Actually, no, let's just turn off these values so it's easier to easier to identify. 5 values. Okay, and now is the amount of value you want to right shift by. So right shift, so it was 5 switches. So let's right shift by 2. So that like only the last 3 bits are 0 compared to the last 5 bits in the original value. Okay, that doesn't appear to be working too correctly. Does it? Maybe I did something wrong by pressing. So let's try again. So firstly, the mode setting is 8. We turn everything on. So this is like the MSB, all on. And then afterwards, let's just turn off 5. And maybe let's do it a simpler value. Maybe I keyed in the wrong value just now. We want to right shift by 1. Okay. So 1 FFDF. Okay, maybe let's try something else. Maybe what if we do 8? We do mode 8 again. We turn everything on. Always on. And then we store it for like all the values, but we don't shift anything. What would be the value at the start? So it'll be like 8. Okay, never mind. Did I key in the right value? Oh, it appears I was using the wrong instruction all along. So that was actually supposed to be apparently SRL somehow. Never mind. SRL? Never mind. I guess we can go back to the SRAs and SRLs later. For now, I can go through AUI PC and LUI. So AUI PC and LUI, what I mainly did was I mainly just set the mode in there such that you can showcase it working. Which is like, let's say I put mode 9. Yeah, mode 9. Set the mode. The values don't matter. And then this is the instruction, like the PC at that point in time. Which it seems about right. LUI is something similar. It's not really that similar actually. It's just you just set the mode and then the other values don't matter. And then the LUI value I sets these upper bits. So just as a quick refresher, LUI is load upper immediate. So in a 32-bit register value, the immediate usually you can load is like a 12-bit value, but there's the upper 20 bits, of course. And so the 12 bits are represented by like 3 hexadecimal characters, and the rest are by this mess. Yeah, so that's LUI. Okay, let me try to get back to SRA. So let's try SRA again. Maybe SRA, let's do something simple first. Like let's say bit shift 8. Bit shift 8 by 1. Okay, so that makes sense. That's SRA. And then now we can do SRL. SRL is a mode value of 8. We can do something similar also. So we set a bit 8. Oops, I said it wrongly. Okay, but never mind. I guess we can just set it again. And then we can like shift it value by 1. In this case, it roughly works out. You can do the math to see why it works out. So SRA, SRL works similarly in the case of, let's say that it's a positive integer represented in 32 bits. So now I guess what will be more interesting is the sign part. What happens if you put in a negative number, which I guess I couldn't really pass the value just now, but it's okay, we can try. So now the mode value is 7 for SRA. SRA, yes. So I set the mode first, turn everything on. And let's say I shift it by 8. No, I shift it by 1 bit. Okay, makes sense. It doesn't really matter. But let's say what happens if I do it for SRL. So SRL, I first set the mode bit. And then afterwards, I just set all Fs. And then all Fs again. But I want to shift it also by like 1 bit. Oh, you notice the MSB is no longer 1. So this actually this will kind of make sense, because like in the previous one, we input in a value of -1, so all the bits are 1, and then we shift it to the right by a value of 1. But because it's still, we want to maintain the sign, so it's like the MSBs are still padded to be 1, so it's still FFFFF. But in this case, in SRL, previously it was SRA. In this case, it's SRL. You don't care about the sign. So you get like all 1s, and then you shift right by a value of 1. And then like you notice like the MSB of 1, I mean, it's lost, it's shifted out. Yeah. And so this is my rough demonstration of CG3207 and our program. So, okay, so this demonstrates all the arithmetic instructions, which is like the add, sub, ni, or add, sub, n, or SRL, SRLL, SLA, LUI, AUIPC. Okay, but in this case, how do you actually demonstrate our branch instructions, our load store instructions for memory? And maybe in this case, I think they suggested that we don't actually, it doesn't really make sense to demonstrate our immediates, which kind of makes sense. If your n is working, you expect your ni to be working. But it's okay, we kind of still demonstrated that somewhat. How? Through our menu logic. So through our menu logic. So let's start with the way input is handled. The way input is handled is through memory mapped IO. So that definitely means that we'll need to like load word from memory to read like the push buttons, for example. LW. And then we also need to store word to like output to the LEDs, output to not just the LEDs but also the 7-segment display. And then add I is definitely demonstrated because that's how we calculated our offsets and our memory locations. And we also demonstrated BNE. BNE is how we keep looping and waiting for user input. So if BNE fails, and then we'll definitely not be able to give us time to input in the correct value. Okay, but we also have BEQ. BEQ is to basically match our mode and see which one is valid. And we have J, which is basically like JL without the link. And yeah, this is CG3207. Yeah, thank you for listening. I don't know why you're listening, but yes.